Alright, let's talk about 2.4. So I have some pre-printed or some pre-typed out notes for this that you can print and use to kind of follow along with this lecture. So let's get to it. So 2.4 is all about applications of right triangles. And before we get started, let me just say this about rounding. And I'll be honest, I'm not sure. I don't think that we're going to use this convention necessarily all semester long, but definitely for this section, we're going to use the concept of significant digits, or you may have heard of it referred to as significant figures in the past. The idea is this. So the idea behind significant digits is that our answer can only be as accurate as the least accurate measurement used in the calculation. So, for example, if we quickly measure a room as 15 feet by 18 feet, even if it's not exactly those measurements, but if that's just a quick estimate, then we can use the Pythagorean Theorem to calculate the length of the diagonal of the room, right? We can say the diagonal squared is 15 squared plus 18 squared, which is 549, and so then we can say the diagonal is the square root of 549, and if you take the square root, you get that it's about 23.430749. However, we should not report that as our answer, because the original measurements that we took were only accurate to the nearest foot, right? So instead, we would round down to the nearest foot, so that if the measurements that we started with were to the nearest foot, then the answer we should give should be rounded to the nearest foot as well. In general, our answer should use the same number of significant digits as the measurement with the least number of significant digits used in the calculation. To determine how many significant digits a measurement has, we use the following rules. So, all non-zero digits are significant. Zeros that are between non-zero digits are significant. Leading zeros are never significant. So 0.02 has only one significant digit, and that's the 2. 0.000515 has only 3 significant digits. It's the 515. Trailing zeros after decimals are significant. So 3.10 has 3 significant digits, while 3.1 has only 2 significant digits. Okay. But trailing zeros before a decimal are ambiguous, right? 2400, we're not sure if that has 2 significant digits, 3 significant digits, or 4. So the context of the problem will usually tell us how accurate the measurement was. But if you wanted something like, if you had something like 2400.0, then you would definitely say that has 5 significant digits, okay? So let's go through a few examples. So we're going to be solving some triangles, right? To solve a triangle means to find the measures of all angles and sides of a triangle. And we're just going to be working with right triangles in this section. So let's solve right triangle ABC if A is 34 degrees 30 minutes and C is 12.7 inches. So first of all, it's a standard convention that when you're dealing with right triangles, angle C is the 90-degree angle. So we might label this triangle ABC like that. And the other standard convention is that the side opposite of the angle gets the same letter, but in lowercase. So this side would be lowercase a, this side would be lowercase b, and this side would be lowercase c. Now we're told that lowercase c is 12.7 inches. And we're told that angle A is 34 degrees 30 minutes. I'm just going to change that to decimal degrees. That's 34.5 degrees, right? 30 minutes is half of a degree. And we're supposed to solve this triangle. So we could do that pretty easily. First of all, we could find angle B pretty easily. We could say B equals 90 degrees minus 34.5 degrees. And 90 minus 34.5 is 55.5 degrees. And as far as significant digits are concerned, it looks like we have 3, right? We have 3 significant digits here, and then 3 or 4 significant digits there, depending on whether that 0 is significant or not. But it doesn't matter because you take the least number of significant digits, which is definitely 3. So we'll say angle B is 55.5 degrees. And now we can find sides A and B by using some trig. So for example, we could say something like sine A. Sine A is opposite over hypotenuse. So sine 34.5 degrees is opposite over hypotenuse. And then solving for A, we would just say A is 12.7 times sine of 34.5 degrees. And let's see about how much that is. 12.7 times 34.5, or sorry, 12.7 times sine of 34.5 degrees. To 3 significant digits, this would be approximately 7.19 inches. Okay. So that's side A. And then side B. For side B, we could do cosine of 34.5 degrees. That equals adjacent over hypotenuse. So that's B over 12.7. So that B is 12.7 times cosine of 34.5 degrees. Now, you could have used angle B. You could have said sine of angle B is B over 12.7. That would also work. Okay. So you would get the same answer if you did that. You're welcome to try that out on your own if you like. But let's do 12.7 times cosine 34.5. So again, to 3 significant digits, this is about 10.5 inches. Okay, and that's how we solve a right triangle. Let's do another example. So this one says solve triangle ABC if A equals 29.43 centimeters and C equals 53.58 centimeters. Again, a picture is going to be really helpful here. So go ahead and draw a picture of the scenario. So this is what we've got. We know that C is 53.58 centimeters and A is 29.43 centimeters. Okay. So I don't know either of these angles, which makes it nearly impossible to solve for them. As for this side, I could use Pythagorean Theorem to find it, I suppose. But let's start with an angle. Let's do, let's say sine of angle A equals opposite over hypotenuse. So that's going to be 29.43 divided by 53.58. That means that A is sine inverse of 29.43 over 53.58. Let's see how much that is. So we've got 4 significant digits here, so we're going to round our answer to 4 significant digits. We're going to say A is approximately 33.32 degrees. Right? That would be our answer to 4 decimal places. Okay, once we know A, we can get B pretty easily. B is going to be 90 degrees minus A, and that's approximately 90 minus 33.32, so 56.68. Okay, so there's B. And now to get side B, we could use, like I said, we could use Pythagorean Theorem, or we could use some trig now, right now that we know what A and B are. Probably using Pythagorean Theorem is going to be a little bit better because when we got A and B, we did rounding to get those. So if we use those answers in a further calculation, we're going to have some rounding errors. So I'd rather use Pythagorean Theorem. I'll say A squared plus b squared equals c squared. So right, and then solve for b. So b is going to equal the square root of, let's see, 53.58 squared minus 29.43 squared is 2004.6915, and then if we take the square root of that, and again we're going to round this to 4 decimal places, so or not to 4 decimal places, we're going to round it to 4 significant digits. We would get 44.77 centimeters. Okay, and that's the answer for that one. Okay, so that's how solving right triangles works. Okay, let's look at another concept called the angle of elevation, or the angle of depression. So the angle of elevation from point X to point Y, where Y is above X, is the acute angle formed by the ray XY and a horizontal ray within point X. Ooh, that's kind of confusing. Let's draw this scenario, right? So what we're saying is we've got X here, and then Y well, that's actually not a very good picture. Here's a good picture. So let's say that X is here, and that Y is some value up here, and it's above X, right? So the angle of elevation is the acute angle formed by the ray XY and a horizontal ray within point X, right? So that's the angle of elevation. So ignore that first attempt, but this is the angle of elevation, right? The angle of depression is similar, but in this case Y is below X. So maybe X is over here and Y is down here. So then the angle of depression is this angle right here, right? Angle of depression. Okay, so that's the idea that we're going after. With that in mind, let's take a look at a couple examples. So number 3 says, at a point A, 123 feet from the base of a flagpole, the angle of elevation to the top of the flagpole is 26 degrees 40 minutes. Find the height of the flagpole. Okay, so we've got some point A. It's 123 feet from the base of a flagpole. So we'll say this is the base of the flagpole, and that this is 123 feet. And then there's a little flag, you know, whatever. And we're told the angle of elevation to the top of the flag, so this angle right here, is 26 degrees 40 minutes. So 26 degrees 40 minutes. And this should be a right angle, even though I didn't draw it very well. We're supposed to find the height of the flagpole, so that would be this value right here. Let's see if we can do that. So I can use tangent. I can say tangent 26 degrees 40 minutes equals opposite over adjacent. That's x over 123. So 26 degrees 40 minutes equals opposite over adjacent. So in other words, x is 123 times tangent of 26 degrees 40 minutes. You can change 26 degrees 40 minutes into decimal degrees if you like. 40 degrees is 2/3, or sorry, 40 minutes is 2/3 of a degree. I'm just going to pop it into my calculator exactly the way it looks, because I have a calculator with the minute button. So I can say 123 tangent of 26 degrees, 40 minutes. So that comes out to, how many sig figs? We've got 1, 2, 3, and so it must be 3 significant digits. So we're going to do 61.8. 0.8 feet. Okay, so x is 61.8 feet. So it's 61.8 feet tall. Okay, so that's that. Let me give you another example, this time an angle of depression. So number 4 says, from the top of a 210-foot cliff, David observes a lighthouse that is 430 feet offshore. Find the angle of depression from the top of the cliff to the base of the lighthouse. So from the top of the cliff, it's a 210-foot cliff. Right? David observes a lighthouse that is 430 feet offshore. So, well, I guess it would have to be a little longer, 430 feet offshore. So here's the lighthouse down here. And it asks us to find the angle of depression. Find the angle of depression, theta, from the top of the cliff to the base of the lighthouse. Right? So the lighthouse, you know, is like standing, but they're asking for the angle of depression to the base of the lighthouse, so to the bottom of it. So it doesn't matter how tall the lighthouse is, in other words. Well, okay. Let's see if we can do that. I think we're going to be using the tangent again, right? We're going to say tangent theta is opposite over adjacent, 430 over 210. That must mean that theta is tangent inverse of 430 over 210, which, by the way, is the same as 43 over 21. Let's see what we get. So tangent inverse of 430 over 210. Ooh. Okay, how many sig figs? It's ambiguous. Could be 2, could be 3. It would be quite a coincidence for this to be exactly 210 feet and this to be exactly 430 feet. So I'm going to guess that they rounded to the nearest 10 feet, right? So probably this is 2 sig figs, right? So to 2 significant digits, we would say this is 64 degrees. Okay, and that's that. I think that's all I have for you in this section. Yep, that's it. So, so that'll do it for 2.4, and we'll see you in the next one.